After studying this module, you shall be able to know the relationship between short run cost and long run cost, learn how long run cost curves are derived from the short run cost curves, learn why the long run average cost curve is U-shaped, know about various economies and diseconomies of scale, derive a cost function from a production function. The long run is a period of time in which all inputs are variable. It is a long enough period such that firms have sufficient time to adjust use of all the inputs in order to produce at the least cost possible. In a way, you can conceive of the long run as a kind of a planning horizon rather than as any particular date in the future. There is a relationship between short run cost and long run cost. You can envisage the long run as comprising numerous short run situations among which a producer may choose. We will study a situation where producers have to minimize cost with respect to two or more variable inputs. In short run, we have already studied the total cost curve, marginal cost curve and average cost curve, whereas in the long run, we will introduce the long run total cost curve and the long run marginal and average cost curves. In this module, we will define and derive long run cost curves. They are derived from short run cost curves. In the next section, we will discuss the long run total cost curve, its derivation and shape. This is followed by the derivation of the long run average cost curve and the reason for its U shape. Thereafter, the long run marginal cost is defined and derived. Long run total cost and its relationship with short run total cost. The long run total cost of production is the least possible cost of producing any given level of output when all inputs are variable. One of the first decisions made by the firm is to decide upon the scale of production. For this, the firm must have the knowledge about the least cost of producing each level of output. Firms can produce a given level of output at minimum cost when it has sufficient time to select an optimal plant size and the optimal proportion of inputs. The table below, table 1, shows long run total cost of production for each output level using the least cost combination of the two variable inputs, labor L and capital K. As you can see in table 1, long run total cost with least cost combination of inputs. In the column wise output, then labor, then capital and the least cost long run total cost has been given to you. The long run total cost LRTC curve is derived from many short run total cost curves. Figure 1 diagrammatically represents the derivation of long run total cost from short run total cost curve. In this figure, the firm faces a cubic cost function. In the long run, a firm chooses the optimal point of production and optimal proportion of inputs for each output level, as it is free to vary the scale of production and input proportions as required. Hence, the long run total cost LRTC is always less than or at most equal to short run total cost. SRTC, that is LRTC, is less than or equal to SRTC. In the short run with K constant, there is an optimal SRTC for every level of output. In the diagram, we see that SRTC1 has K1 level of capital, SRTC2 has K2 and SRTC3 has K3, etc. In the long run, K can be varied. So, the long run represents the least cost of different quantities of output and it is traced by taking the points of tangency of different SRTC curves associated with different levels of output. Therefore, technically the LRTC is said to be an envelope of the corresponding SRTCs. A short run cost function is typically represented by SRTC is a function of Q, small w, small r, K, equation 1, where W wages and R rent are price of inputs. A family of short run cost curves are generated by allowing K to vary while holding W and R constant. A long run curve follows the condition given in equation 1, along with the condition that the chosen K is cost minimizing for any level of output. The first order condition for this minimization is as follows: delta SRTC in bracket Q small w small r K upon delta K is equal to 0, equation 2. Together, equations 1 and equation 2 will generate the long run cost curve. The shape of the LRTC is an inverse S with the following characteristics. A. LRTC passes through the origin. In other words, it does not have an intercept as there is no fixed cost. Since there is no fixed cost, therefore LRTC is 0 when output is 0. B. LRTC has a positive slope. It means it costs more to produce more. C. LRTC initially increases at a decreasing rate and then it tends to increase at an increasing rate. The reason behind this is returns to scale. Recall, you have learned about this concept in earlier modules. Initially, we have increasing returns to scale leading to a slow increase in cost, whereas later on decreasing returns to scale sets in leading to a speedy increase in cost. The constant cost case. There is a case when the production function exhibits constant returns to scale. In that case, in the long run, the costs are proportional to output produced. Figure 2 represents such a case. In this case, the LRTC is a straight line through the origin. Figure 2 shows constant returns to scale cost curve. Next is long run average cost and its relationship with short run average cost. Long run average cost lack the concept. Long run average cost lack refers to the minimum possible per unit cost of producing different quantities of output in the long run. Lack is determined by dividing the long run total cost LRTC by the corresponding level of total output. It shows the lowest cost possible when all inputs are variable. Lack is given by lack is equal to LRTC upon output Q, equation 3. Now, table 2 shows the long run average and marginal cost with least cost combination of inputs. In table 2, we can see that long run total cost is increasing as output increases. However, the long run average cost decreases when output increases from 20 to 30 and then rises. When output increases from 30 to 40, the associated long run marginal cost LMC is also rising as output goes up. Note that the LMC is less than lack when lack is following, but LMC is greater than lack when lack is rising. This is as per the relation between marginal and average quantities that we studied in earlier modules, and as per this relation, when lack is minimum, lack is equal to LMC. Next is relationship between long run and short run average cost. Short run costs are based on the fact that capital is fixed and labor is variable, and hence in order to increase output only the variable input labor has to be increased, whereas the long run costs are derived based on the assumption that all inputs are variable and therefore all adjustments can be made in order to achieve the minimum cost combination of inputs to produce different levels of output. Figure 3 demonstrates short run average cost curve for different levels of output. The lag is derived from various short run average cost curves SAC. In the short run, a firm uses a certain plant size with fixed K and hence a certain SAC. Figure 3. Suppose a firm is at SAC 1. The minimum of SAC 1 occurs at Q1. After Q1, the average cost starts rising. If the firm plans to increase the output in the long run, the question arises, what would be the ideal plant size for a higher level of output? Till Q11, SAC1 is the least cost plant size and hence the most profitable one. But as output goes beyond Q11 or Q11, SAC1 gives higher unit cost of production than a bigger plant size SAC2. Hence, beyond Q11, the firm will shift to SAC2. Similarly, SAC2 would be most profitable till Q22 and after that SAC3 will be more efficient as it will give lower unit cost of production. In general, there is an optimal plant size and therefore a short run average cost curve associated with every level of output. In order to trace lag, we will take the envelope of all possible SAC, that is, lag is tangent to each SAC at some point, figure 4. That indicates the plant size and least cost of production for the corresponding output level. Hence, the lag curve is also called an envelope curve because it encloses all the SAC curves. Figure 4 shows the derivation of long run average cost from short run average cost. Q star is the output level at which lag is minimum. At this point, the minimum of SAC is tangent to the minimum of lag. To the left of Q star, the point of tangency of SAC and lag is on the falling part of LAC. This is because lag is negatively sloped till Q star and hence it will be tangent to the negatively sloped part of SAC. Similarly, to the right of Q star, the point of tangencies between SAC and lag will be on the rising part of both curves. It is important to note that the lowest point on each SAC curve need not be the point of its tangency with the lag curve. The lowest point on a SAC curve is tangent to lag only at the minimum point of lag. Therefore, Q star is the only point on lag where the short run plant is optimally utilized. That is, production occurs at minimum SAC. Lag is also known as the planning curve because with the help of this curve, a firm can plan its scale of operations so as to produce at the minimum possible unit cost. The long run average cost curve is a planning curve as it helps a firm to plan the expansion of its output. A. Kotsiani. Next, we will discuss about the shape of lag. The long run average cost curve is U-shaped, essentially the same shape as the short run average cost curve, although it is much flatter than a SAC curve. The reason for this should be clear from the derivation of the lag discussed above. It represents the least cost of producing each output level when the scale of production can be changed as there is no fixed input in the long run. As discussed above, the lag falls, reaches a minimum and then rises. What is the reason behind this shape? It is because of economies and diseconomies of scale. The lag falls when a firm experiences economies of scale and rises when there are diseconomies of scale. Now, we will discuss upon economies of scale. A production process is subject to scale economies when an increase in output leads to a decrease in the average or per unit cost of production. There are numerous examples of economies of scale. Example, an increase in the scale of production often leads to bulk procurement and hence cheaper raw materials for production. The falling part of lag is due to the fact that economies of large scale production become available as it expands output. Economies can be available in the form of internal economies like labor economies, managerial economies and technical economies. There are various external economies as well as that become available to the firm. Example, when the whole industry becomes bigger, these may be available in the form of access to improved infrastructure. Example, transport and communication facilities, better supply networks, logistics support, better financial facilities, etc. However, as a firm continues to expand, it reaches a stage where economies of scale are exhausted and eventually disappear. Thereafter, diseconomies of scale set in. Next is diseconomies of scale. A production process is subject to diseconomies of scale when unit cost of production do not decrease, rather they tend to rise with increased level of production. As firms become large beyond a point, unit cost of production start rising with increase in output. As scale economies no longer function. As diseconomies of scale come into operation, the lag curve starts rising. Diseconomies may be due to various reasons. For instance, the limited capacity of the management to manage the production process efficiently beyond a point is an important reason for diseconomies of scale. Often, management capacity remains fixed as it may not be easy to enhance skilled management staff as output expands continuously. In this case, it becomes difficult to manage the increase in labor and capital units along with other factors involved in the production process. Difficulties in coordination may result in inefficiency leading to increased cost in the long run. Besides this, there may be some infrastructures which cannot be expanded even in the long run. This may lead to escalation in cost leading to upward sloping portion of lag. Thus, as a result of first economies and then diseconomies of scale, a firm faces a U-shaped lag over its range of output in the long run. Next is long run marginal cost curve. The concept and derivation. The long run marginal cost LMC curve shows the additional cost incurred in the long run when one more unit of output is produced. It is defined as LMC is equal to delta LRTC upon delta Q, equation 4. It is the change in the long run total cost per unit change in output. It is derived from the short run marginal cost curves SMC. In figure 5, we look at the process of deriving LMC from SMC. Figure 5 demonstrates average and marginal cost curves. The LMC curve is derived as follows. For each point of tangency between SAC and lag, we get an output level and the SMC for that level of output gives a point on the LMC. We get the LMC by joining all such points as shown in figure 5. First, we plot the SAC and trace the lag. Following this, we draw the SMC for each SAC. For example, for SAC1, SMC is the marginal cost curve. The tangency point of SAC1 and LAC is at G, and the marginal cost of producing the corresponding output Q1 is given by G dash. Thus, point G dash is a point on the LMC. Similarly, we get the marginal cost for SAC2 as H dash, SAC3 as E and SAC4 as J dash. We join all these points, that is G dash, H dash, E and J dash, in order to obtain the firm's long run marginal cost curve. The locus of all these points gives the LMC because it corresponds to the tangency points of the SAC and LAC at which the firm produces in the long run. That is, SAC is equal to LAC at that level of output, and hence SMC and LMC are also equal. Point E is the minimum of LAC, which is also the minimum of SAC3 and also the intersection point of SMC3 and LMC. Hence, at this point, SAC is equal to LAC is equal to SMC is equal to LMC, equation 5. That is, all the cost, short run and long run average as well as marginal cost are equal. This is the optimum point of production for any firm where long run average cost of production is minimized. The minimum of LAC curve is the most efficient point of production in the long run with minimum unit cost. At this point, SAC is equal to LAC is equal to SMC is equal to LMC. Next is the constant cost case, constant returns to scale. Sometimes it is convenient and realistic to assume constant returns to scale over the entire range of output. In this case, LAC is a horizontal straight line and is equal to LMC at all output levels. The firm neither experiences economies of scale nor diseconomies of scale. They experience constant returns to scale when, with an increase in the number of units produced, the average cost of production remains constant over the relevant range of output. In this case, output expansion causes neither a decrease nor an increase in the average cost of production. Next is deriving a cost function from a production function. The Cobb-Douglas production function and its corresponding cost function. Suppose a firm faces total cost C is equal to small r into K plus small w into L, and suppose it has a Cobb-Douglas production function as in equation 6 that was introduced in the earlier modules. In this case, we can derive the cost function for the firm by constraint minimization, wherein the firm minimizes total cost for producing a given level of output, say Q0. This is shown below. Cobb-Douglas production function Q is a function of K and L is equal to K raised to the power alpha L raised to the power beta. The relevant Lagrangian expression for cost minimization subject to a given output level Q0 is Lagrangian is equal to small r K plus small w L plus lambda in bracket Q0 minus K raised to the power alpha L raised to the power beta. The first order conditions for minimum are: first, delta Lagrangian upon delta K is equal to small r minus lambda alpha K raised to the power alpha minus 1 L raised to the power beta is equal to 0. Second, delta Lagrangian upon delta L is equal to small w minus lambda beta K raised to the power alpha L raised to the power beta minus 1 is equal to 0. Delta Lagrangian upon delta lambda is equal to Q0 minus K raised to the power alpha L raised to the power beta is equal to 0. Equation 8. Solving these yields small w upon small r is equal to beta K raised to the power alpha L raised to the power beta minus 1 upon alpha into k raised to the power alpha minus 1 L raised to the power beta, or small w upon small r is equal to beta into k upon alpha into L. From this we get the value of k as k is equal to alpha into small w upon beta into small r into L. Equation 10. Substituting into the production function gives a solution in terms of L, Q, small w and r. Q is equal to alpha into small r upon beta into small r whole raised to the power alpha into L raised to the power alpha plus beta. Equation 11, which gives L is equal to Q raised to the power 1 upon alpha plus beta into beta upon alpha whole raised to the power alpha upon alpha plus beta into small w raised to the power minus alpha upon alpha plus beta into small r raised to the power alpha upon alpha plus beta. Equation 12. Similarly, the expression for k is given by k is equal to q raised to the power 1 upon alpha plus beta into alpha upon beta raised to the power beta upon alpha plus beta into small w raised to the power beta upon alpha plus beta into small r raised to the power minus beta upon alpha plus beta. Equation 13. Using these equations and using cost is equal to small w into L plus small r into k, we get the cost function as cost is equal to q raised to the power 1 upon alpha plus beta into t into small w raised to the power beta upon alpha plus beta into small r alpha into small r raised to the power alpha upon alpha plus beta. Equation 14, where t is equal to alpha plus beta into alpha raised to the power minus alpha upon alpha plus beta into beta raised to the power minus beta upon alpha plus beta, which is a constant involving only the alpha and beta. Another example of cost function is the one corresponding to a fixed proportions production function. Q is the minimum of alpha into k and beta into L. It can be shown that the cost function for this production function is given by cost is equal to q in bracket small r upon alpha plus small w upon beta. Equation 15. Next, summary. The long run is defined as a period of time which is sufficient to bring about necessary changes in the scale of operations by varying all the inputs used in the production process. All the inputs are variable in the long run. Long run total cost of production is the least possible cost of producing any given level of output when all inputs are variable. We can derive long run total cost curve from the family of short run total cost curves. The long run average cost lag refers to minimum possible unit cost of producing different quantities of output in the long run. It can be traced by forming an envelope of the short run average cost curves for every level of output produced. The U-shape of the lag occurs because initially there are economies of scale followed by setting in of diseconomies of scale. The long run marginal cost curve is derived from the short run marginal cost curves corresponding to the tangency points of SAC and lag. In case of constant cost, constant returns to scale, the long run total cost is a straight line passing through the origin and the corresponding long run average cost curve and long run marginal cost curve is a horizontal straight line parallel to the output axis.